Well, hello. Welcome to statistics. So we're going to start with chapter 3. If you look at the syllabus, you'll see that this is the starting point. We're going to be looking at several key concepts here. We're going to introduce the concepts of populations and samples, and then we're going to calculate some important measures on samples and populations using several formulas that we'll see throughout the course. Now, before we get started, I just want to point out that you can do a lot of these problems on a calculator. In particular, you might have the TI-84 series. If you do, that's good because we'll be using it a lot. You may also have the updated version, which is this TI-84 plus CE. Yeah, that nice new one. Either one will do the job. Occasionally, there are differences between these two calculators, and I'll point that out as we go along. But either one of these will be fine. If you also have the slightly older version, the TI-83, that will work as well too. There's just one or two functions that it doesn't have, but I'll point that out again as we go along so that you should, if you have one of these calculators, have no difficulty at all coming up with the correct solutions. As you get into the deeper and more complex material, the calculators will become progressively more important. In the early days, like here, it's not quite as important, but eventually there'll come a point where the calculators will become more or less indispensable. And it's not just for this class. I suspect that most of you who are in this class will also be in stats decision making. And that's when the calculators really start to become important. So even if you're only just taking stats 1, it still might be worth your while to go out and get your hands on an excellent calculator like these, because you could use it for your other classes as well. In fact, you may not be aware of it, but these two calculators have several financial apps that you could use in a class like corporate finance. So it's a good investment. And from what I've been told, a lot of you may have had one since high school, and that's good. All right, that's very good. Now, in the meantime, why don't we start the new material today? And so, as you know, this is an asynchronous class, which means that you'll watch these videos when it's convenient. And periodically, there will be assignments for you to work on. And then every so often, we'll have a test. And so sometime around the first week in August, I believe, the course will be over and you will learn a full semester worth of statistics, which is hugely helpful because it will probably save a lot of space in your schedule in the fall. And certainly make your, I mean, the worst thing you can have is an extremely hectic schedule. This should help you reduce the hectic, the complications with your fall semester. So anyway, and the reality too is that this material is so useful no matter what business discipline you end up studying. If you're in Gabelli, it's going to be helpful. Statistics is everywhere. Every business discipline depends very heavily on statistics, but some more so than others, of course. Finance in particular is heavily based on finance. Also, if you're not in Gabelli, if you're studying, let's say, economics, economics is also heavily based on statistics. So anyway, look at it. This is going to be a very useful course, and it's also going to be interesting, I hope. I'll try my best to make it as interesting as possible, but there's a lot of calculations to do. There's a lot of formulas, although I'm going to try to avoid having you memorize a lot of formulas. You still have to understand how they work. Otherwise, the thing is you can forget formulas if you memorize them, but once you understand them, you'll retain that forever. Okay. So what are we doing in this chapter? Well, first of all, we're starting at the beginning by looking at the concept of samples and populations, and we'll be using these ideas throughout this course and stats decision making. So we start out by defining what we mean by a population and a sample. Now, population, the word population, as you know, often is used to represent a group of people, but we're using it in a more general sense than that. In general, a population is simply a collection of measurements or outcomes of interest. So let's say, for example, the US government is analyzing the average life expectancy of American citizens. And so in order to do this properly, they need to gather information about the ages of the people who live here So the population that they're studying is not the actual American people themselves, but their ages. You can imagine the population is this gigantic set of approximately 330 million ages. And they need to know, if on average people are living longer, if they're living, their ages are increasing, if the population itself is aging, among other reasons, because the Social Security system will have to spend more money if people live longer. And so they have to think about this in advance. They have to plan for this years in advance. So it's important to know what the age of the average American citizen is. Now, the unfortunate reality, though, is that 330 million people is a lot of people. It could take a long, long time to actually gather together the ages of everybody who lives in the country. So what do they do instead? Usually what they'll try to do is, in order to save time, is draw what's called a sample from the population. And the sample itself, think of it as a subset of the population. In other words, it's a smaller piece of the entire population. Now, sampling is a very important area of study in statistics. There's many ways we could go about this. We're going to keep it simple here. We're going to essentially assume that when we draw samples, we're essentially randomly choosing elements from the underlying population, that there's no pattern to the choices that we're making. So, let's say we choose a sample of, or the government, for that example I was just giving you, randomly chooses 10,000 people in the United States to represent the population for their study of ages. They're going to make sure that those people are randomly scattered around the country so that their ages do reflect the overall population. If they choose badly, they're going to end up with bad results. Okay, so for example, what if they accidentally only choose retired people for their sample? Then the age in that group is going to be higher than for the country as a whole, and the results will be meaningless. So a sample is a smaller part of the population that's chosen to reflect the properties of the population. We're going to assume that this is being done correctly, but with the understanding that if samples are not chosen correctly, then the results will not be very meaningful. Now, by the way, just as a quick side note here, the word subset refers to set theory. So we're going to take just the quickest review here of sets real fast, or at least the concept of subsets. We'll get more reviewing of set theory later on. So here we are. We have three sets, A, B, and C. Now, if you notice, a set is nothing but a collection of elements. A is the set that contains the elements 1 through 5. B is the set that contains the elements 1 through 3. And C is the set that contains the elements 5 through 7. Now, what does this mean to be a subset? Well, you can see that B could be defined as a subset of A because all the elements in B are also elements of A. So therefore, we say that B is a subset of A. On the other hand, the same can't be said for C because the 6 and the 7 are not elements of A. The 5 is, but the 6 and 7 are not. And so that means C is not a subset of A. Now, if you want to use the formal notation, you may have seen this before, that this is the symbol for is a subset of. And the symbol that tells us that something is not a subset of another is the same symbol, but with a slash through it. So in other words, B is a subset of A, but C is not a subset of A. So what that means then is that if A is some kind of a population, B would be considered a sample, or could be considered a sample. It's one possible sample that we could draw from population A, but C is not. Okay, it's not possible to draw sample C from that population A. Anyway, for now, that's all we need to discuss for set theory. We'll get back to it later on in the course. Here's another quick example. Let's say we've got a really huge university like Ohio State. Over 100,000 students go there. The school wants to estimate what the average GPA is for all their students. Well, the population is 100,000 GPAs. That's a lot of GPAs. So what they might be tempted to do, just to come up with a rough estimate, is pick a random sample of students and look at their GPAs, and whatever the mean GPA is in that sample, they'll use it as an estimate of the population GPA, or for the entire student body. Now, how close they get to the actual population GPA depends on how carefully they chose that sample, and also how large the sample is. The larger the sample, the closer it is likely to reflect the underlying population. All right, now, once we have our data, whether we're using the population or sample, either way, we're not normally interested in the actual raw numbers. There's usually certain properties that we're interested in. So we're going to start by defining a set of what are called measures of central tendency. And these are some measures that will help us understand the properties of either a sample or a population. And so what we're trying to establish here is, what is the center or middle of this data? That's essentially what we're trying to do here. And we can do this in several important ways. And each of these has its own unique advantages and disadvantages. Okay, none of them is perfect, but you'll see when you see the list, you'll probably realize that you've heard of all these terms before. Well, let's take a look at them. We have the mean or average, we have the median, and we have the mode. The one you see most often is the mean, of course, or average. Everybody's calculated averages. For example, you might want to know what is the average cost of gas in the city that you live in, for example. The median is a little bit different. It's reserved for special cases, which we'll look at in a few minutes. And the mode is something that's not used quite as often, but it also does have its place. Now, before we go any further, I want to mention something important here. One key detail that I want to mention is that measures of central tendency can be used for both samples and populations. So we will always make a distinction between each case, except there are some exceptions. In many cases, the actual calculations are the same for both samples and populations. Okay. Although the terminology, the notation may be different. Okay, in other words, we may use different symbols for sample measures and population measures. But the bottom line is, how do we actually calculate these measures? And in many cases, they're the same for both samples and populations. So we do want to remember which is which. In other words, when you calculate something, it's important to know what you're actually calculating and think about whether it is based on a sample or a population. Otherwise, you're bound to make mistakes. All right, it's very important to know what you're applying these techniques to. All right, now, so we're going to start by looking at the mean of a sample. We're going to go through our list one at a time, and in each case, we'll discuss how would we do this for a sample and how would we do this for a population. Okay, so we'll start with the mean of a sample. Now, I'm going to introduce you to some new notation. Oh, sorry about that. And we're going to see this notation quite often in the future, so it's awfully important to get this straight right now. The sample mean can be expressed with this scary-looking equation. And so what we want to know is, what exactly is this equation telling us? All right, well, let's take a look at it one piece at a time. This first part is called X bar. As you can see, why? And it is used to represent the sample mean. Now, what we're assuming here, if you notice right here, the sample contains n elements. In other words, it could be any number. It could be 3, it could be 7, it could be 52. N represents what we're going to call the sample size. So we're going to assume that the elements in our sample have all been supplied with an index, which ranges from 1 to n. Okay, so just as an example, you might have something like this: x1, x2, x3, all the way up to xn, whatever that happens to be. So if you have 10 elements in your sample, the indices that you'll see or applied to them are the integers from 1 to 10. That makes things a lot easier for us to keep track of them. If we try to have a separate letter for each element, we run out of letters very quickly. Instead, we'll choose a letter like X, and then we'll have an index attached to it. So that way we can have any number of elements we like. Now, another important part of this formula is right here. We're going to see a lot of this in statistics. So first things first, this symbol is actually a Greek letter. It's the uppercase version of sigma. The Greek alphabet, like our alphabet, which is basically the Roman alphabet, has cases, in other words, lower and uppercase letters. That is something unique, I believe, to Western languages. I've asked a lot of people about this who speak other languages, and this is something that apparently doesn't show up in other languages, the concept of case. So, but the Greeks have it, the Romans have it. So we're going to use that here. Let me just make this a little neater. Okay, and so this is often referred to in math as the summation operator. And the reason for that is because it's telling us to add something up. It's really that simple. And so the way it's written, we'll be able to figure out what exactly we're adding together. So the way it's written right now, we can interpret that to mean, very simply, let's see, I'll just sneak in another slide here so we can expand on this. So what you're doing is you're running through the entire list of elements in your sample, and you're just adding them up. So if we have n elements in our sample, this notation says, take your x's and add them up. And you notice by the index, I equals 1 to n, that's how we know that we start at 1 and we end at n. By the way, it doesn't have to start at 1. Often it does, but not always. It could start at 0, for example. And also it's understood by the way it's written, they were increasing one at a time. If you notice, it goes from 1 to 2 to 3 to 4 up to n. Again, it doesn't have to work that way. There are ways that we can, let's say, add 2 every time. Let's say we have x1, x3, x5, that type of thing, but not here. Here we're just interested in the first n elements, and we need to know the sum. So that's what the summation operator is telling us. So now that you know that, if you look at this formula again, you'll see that it's really a very simple concept. The sample mean. What it's telling us to do is something that you intuitively already know how to do. It's the sum of all elements in the sample divided by this number of elements in the sample, or the sample size. And so everybody, I think, understands this intuitively. I mean, imagine yourself needing to calculate, for some reason, the average incomes of all the people who live in a town. Let's say there's 100 people in the town. You would add up all their incomes and you divide by 100, and that would be your answer. It's that straightforward. So this is just a formal way of expressing that. And the beauty of this type of formula is that it applies in every situation. It doesn't matter how much data you have or what the data is. This formula will always work. And we can build on this to create more complex formulas, as you'll see, with this summation operator. Well, all right then. That wasn't too painful. Yeah. Now, here's our first specific example. Let's say we have a sample of some kind where these are the 5 elements. Now, it almost doesn't matter what these numbers represent. For our purposes, we just want to see how to use our techniques to come up with this 3 central measures of central tendency. But, you know, you could easily imagine these could represent, for example, temperatures or something like that. So first things first, what if we applied the summation operator to this sample? What would we get? All right, so now you've noticed the elements are indexed 1 to 5, which is what we would have expected. That means that n is 5. And so the sum is written in the following way. In the first case, we have just the general expression. And then the second case, we have our specific case. And so you can see it adds up to 10. All right. Now we can use that information to come up with our sample mean, because all we have to do now is divide by 5, because that is our sample size. So in other words, and that's all there is to it. So in other words, given this set of data, the sample mean is 2. Because the sum of the elements is 10, there are 5 elements, that ratio is equal to 2. So the average, if these are temperatures, let's say the temperatures in the first week in January in Minnesota, then the average temperature that week was 2 degrees. Now, I quickly want to show you other ways we can put this summation operator to use. We will need these in some of the formulas we'll see later on. Let's say that we don't need to know the sum of the x's, but the sum of the squared x's. That could happen. So how do we write that? Well, remember, the sum of the x's is written like this. If I need to square the individual elements, this is what I do. I write it as xi squared, and that tells me that I'm going to square each of these elements and then add them up. So using the same data we had in that last example, 2, -1, 3, 5, and 1, I'm going to not add them up directly. I'm going to square each term before I add them up. And you can see that means the sum of the squared x's is 40. So you can see this opens up a lot of possibilities. I can do a lot of things with the summation operator, a lot of things. And we'll keep seeing this throughout this course in stats decision making. Now, here's another thing we could do with this summation operator. What if we have a formula that requires the following? We need to add up all the terms in our sample and then square the result. Okay, so you can see the difference here. In this slide, we square, then add. In this slide, we add and then we square. So you can see what happened here is that I added up all my elements, which means I have 10 here, and then I square 10 and I end up with 100. So you can see these are 2 very different cases. So we have to be a little careful with the way it's written. If you notice in the second case, I've got the parentheses around the summation, and then I have the square. That's how I know which is which. Now, this next one is a little more challenging, but it makes perfect sense once you understand what it's doing. And we will definitely need this very, very soon. What could it be? Well, what you have here is, if you notice, I've got some k here. K is a constant. It doesn't matter which constant it is. What I have to do now is several things. For each x in my sample, I have to subtract this constant. Then I square the difference. And only then do I add them up. So I have to subtract, square, and then add. It's a three-step process. That's what this is telling me. It's a very compact way of saying, take each x in your sample, subtract the same constant k, square the differences, and then add them up. Oh my God, it sounds very challenging, but when you've done it once or twice, it's really not that bad. So let's go back and revisit the same data set we've been working with, and let's just use 3 as our constant. So it'd be written like this. You notice how the k has been replaced with a 3. And so I have my elements. Remember, this is our x1, x2, x3, x4, and x5. In each case, I subtract the 3. So what I've done here is I've evaluated the subtraction, the differences, before I square them. I think that'll make it easier to avoid making mistakes. So in other words, 2 minus 3 is -1. -1 minus 3 is -4. 3 minus 3 is 0. 5 minus 3 is 2. And finally, 1 minus 3 is -2. Now I square them. And I get 1 plus 16 plus 0 plus 4 plus 4. And I ultimately end up with 25. So there's so many more of them, but these are the 3 that we might actually need during this course. There's all kinds of crazy things you can do with the summation notation, but we will stick with the basics here. All right. Now, with all that being said, we can go back to original example where we're simply trying to calculate the sample mean of those 5 elements. And this is the final result. And this is, as I mentioned before, we've already seen that the sample mean is 2. All right, so whatever the sample represents, the mean is 2. All right, now, I did mention before that for every measure, we would like to make a distinction between the sample version and the population version. This is one of those cases where the 2 are calculated the same way, but the notation is different so that we know which is which. So I'm going to show you the formula, and we'll point out the differences and the similarities as well. All right, here we go. So now remember what we had before. This is our sample mean. And you can see they look very similar. Well, what do you see here? Another Greek letter. This is the Greek letter mu. It corresponds to the Roman M, and it is used to represent the mean of a population. The only other thing that's really different is if you notice we're using capital N's here instead of lowercase. So the convention we'll be using going forward is that lowercase n is the sample size and capital N is the population size. Why do we need a separate letter for each? Because there are going to be formulas later on that include both of these. So we have to have some way of telling them apart. So we're going to use this convention. N is the lowercase n is the sample size. Capital N or uppercase N is the population size. Now, one other thing I want to point out here is if you notice, X is one of the letters that we use every day. This is taken from the Roman alphabet. This is taken from the Greek alphabet. So the convention we'll use going forward is this. We're going to use okay, so let me just make a note of this. We will use Greek letters to represent population measures and Roman letters to represent sample measures. And that's how we're going to be able to tell them apart. That's the standard practice in statistics. So sometimes that's the only difference. Now, if you look carefully at these formulas, though, if you notice, you're doing the exact same thing, aren't you? In the left-hand side, you're adding up population elements. On the right-hand side, you're adding up sample elements. And then in the left-hand side, you're dividing by the population size, and the right-hand side, it's the sample size, but you're still following the same exact steps. Okay, the only thing that's different is the notation. So they're really the same concept, except one is applied to populations and one is applied to samples. There will come a time soon enough when the two formulas are actually different. Okay, not just the notation, but the actual formulas. Not here, though. All right, so now here's an interesting type of mean that we might encounter. Not all situations are the same. We may have different types of data, and sometimes we might have a group of data where, let's say, many of the sample elements are repeated multiple times. A good example of this would be, let's say, GPAs. There's only so many letters that they have. And so when you're calculating GPAs, what do we have? We have A minus, A plus, no, A plus, A minus, etc., all the way down to F. And so there's not that many different letters. And so within even one person's 4 years of college, you're likely to get a large number of A's, B's, C's, whatever. So when we have a lot of repeated values, it's usually easier to use the following approach to calculate a mean. And it's called a weighted average. It's perfectly suited for cases where there's many repeated observations in a sample or a population. The idea here is that you're trying to capture the impact of some observations compared to others. Anyway, so the formula for this is going to be a little different. Let's start by looking at the weighted average for sample. Oh, okay. Now, you see, it got a little bit more complicated. What's new here is this W. This is the weight, which you could also think of as a frequency. Of sample elements xi. Okay, notice how many times did this happen in your sample? What we're doing here is you're multiplying each x by its own weight. And then you add them up. Okay, in other words, and we'll see some examples of this. For each x, there's a weight. Multiply them together. For each sample element, multiply each by its own weight and add them up. Down here, all you have is the sum of the weights. So it's a little bit messier, but it also can be much more straightforward than what we just did. All right, now we also have an equivalent version for a population, and you'll see that it's exactly the same procedure, only with a slightly different notation. All right, so let's see what the population version looks like. In fact, I'm going to copy this into the next slide so you can see them side by side. All right, so the one on the left is the sample weighted average. On the right, of course, is the population. Weighted average. I have to abbreviate it because I'm running out of space. How do you know which is which? Oh, that's right. The population measure uses the Greek letters, and we have the uppercase N's here. But that's it. Again, that's the only difference. So it's the same thing in both cases, only with different notation. All right, so let's look at a very simple example of this. Imagine that there's a really small lottery taking place, not one with millions of dollars worth of prizes. And so we've got, within this lottery, there's a single prize worth $1,000. We have 10 prizes of $500 each and 100 prizes of $10 each. So if you win a prize, what is the average value of that prize? Now, the one thing we're not going to do here is add up 1,000 plus 500 plus 10 and divide by 3. Why not? Well, here's why. Because there's a lot more $10 prizes than $1,000 prizes. We have to find a way to take that into account. Otherwise, the result we get will be very badly distorted. So how do we do that? Oh, wait a minute. This is a perfect opportunity to use the weighted average, because the 3 prizes do not occur with equal frequency. We could, now by the way, you could actually do this the same way we did earlier by just writing out these prizes. What we have here is a single $1,000 prize. And then we have a bunch of $500 prizes. And I'm not going to write them all out, but and then for the tens, there's 100 of them. So altogether, you'd have 111 prizes in the numerator, and you could divide by 111, and you get the right answer. But man, and what a nuisance that's going to be. Imagine adding up 111 different numbers. What do you think the odds are of making a mistake? Pretty high. So instead, we use this more clever approach, where what we do is we take the 3 prizes and we create weights for them. The weights are the frequencies. So remember, we were told there's a single $1,000 prize, there's 10 $500 prizes, and 100 $10 prizes. So now we're going to plug these into our formula for the population. We're going to treat this as a population because this represents all the prizes in the for the lottery. But it makes no difference to our calculations whether it's a sample or a population. So let's do it. So here's what we have. In the numerator, this is what we're being told to do. So you've actually got, oh, I should have written down the intermediate steps. In the numerator, you've actually got 7,000 over 111. And that's rounding to dollars and cents, of course, 63.06. So the average prize in this lottery is $63.06. Now, if you didn't know how this works and you just simply added them up, like way back in the beginning, you might have been tempted to say, well, it's 1,000 plus 500 plus 10 divided by 3. If you'd done that, you would have gotten $503. Why would it be so high? Because you're weighting each of the 3 prizes equally, which we know is not the case. There's a lot more $10 prizes than $1,000 prizes. So it stands to reason that the average will be much closer to 10 than 1,000. And that's exactly what we see here. 6,306, much closer to 10 than 1,000 because of the weights. All right, now here's an example that you're all familiar with, GPAs. Now, as you know, or maybe you've never noticed this before, but the grades on the right, the letters correspond to numbers, but I'm sure you noticed this when you looked at your schedule, not every class is worth the same number of credits or credit hours. So when they calculate your GPA, like here, for example, they're not going to simply add up these numbers and divide by 4. Why not? Because the calculus and physics scores are worth more than the English and psychology grades. And that has to be taken into account. But how do we do that? There's no frequencies here, by the way. These are not frequencies. These are weights that are attached by the school to represent how much time you've spent in the classroom. So how do they do this? Well, here's what they're going to do. These are the X's and these are the weights. So what we're going to do is calculate the weighted average for these classes. All right, so in other words, here's the weights, the 4 classes, and the 4 grades, the averages, the GPA. I guess they're called, used to be called quality points. I don't know if they still call them that or not. Anyway, so let's see how this works out. So using the formula, again, your semester will treat that as a population. It doesn't really matter whether we call it a population or a sample. So we went through. And as you would expect, multiplied the weights by the grades, which are the X's. Down here, we simply add up the weights. And so you end up with 47.9 over 14. Your GPA is 3.42. And that's how they do it. That's actually how they do it. So if you always wondered about that, now you know the secret is out. The cat is out of the bag. This is how they calculate your GPA. Now, I do want to point out that if you didn't know about this and you tried to do this yourself, suppose you didn't know any better. You said, well, I guess they're just adding these up and dividing by 4, right? If you'd done that, you would have gotten a total of 13.3 over 4, which is 3.325. Wait a minute, but didn't it turn out that your GPA is actually 3.42? Yes. So using this approach, you would have actually cheated yourself out of some points. Why is this happening, by the way? Because you did the best in the classes that had the highest number of credits. So your actual GPA is higher than a simple average. If it had been the other way around, though, then this approach would have given you a higher GPA. So, you know, it would have been lower because it comes down to doing your best in the high credit classes. So anyway, now we know how GPAs are calculated. All right. Now, if you remember that list we saw of measures of central tendency, the next one on our list was median. Let me just go grab the list. Yes. So let's do that right now. Now, the median is a little different. Here, what you're actually trying to do is imagine you've got a bunch of data. And let's say it's a bunch of ages. Let's say, I don't know, these are all the people who are at your house for Thanksgiving, and those are their ages. Okay. So the median is basically a dividing line between the lower and the upper half of the data. It's like, imagine that your house you've got two tables. Each one is only big enough for 4 people. And so you got to figure out a way to decide who sits where. So you say, all right, what the heck? The youngest people will sit at one table. The oldest people will sit at the other table. Well, how would you know which is which? Yeah, you divide the ages in half. And by the way, if you notice, what I had to do here is the ages are actually sorted from low to high. So when you calculate a median, first thing you'll have to do is sort it out. And then you can figure out how to find that dividing line between the lower half, where half the elements are below the median, and the upper half, where half are above. So whatever this number is, it cuts the data in half. Now, how is this done? By the way, in this particular case, it's going to end up being 24. What's happened here is that this is halfway between 22 and 26. All right. So in other words, we would call that the median because half are below and half are above. All right. So let's do an example. Now, this is the data set we had earlier. So we've already seen that the mean is 10. But what about the median? So the first thing we have to do, as I mentioned, is sort the data from low to high. And there we go. That's what happens when they're sorted. Now, how do we divide the data? Well, it turns out, I'll just mention this right now, that the technique used to calculate a median depends on whether the data set, and that means either a sample or a population, has an even number of observations or an odd number of observations. So those are the two cases we have to consider, even and odd. Okay, the techniques will be a little bit different. So in this example, we have an odd number of values, 5. So this is the simple case because all we have to do is find the data element that's in the center. It's right there. The 2 is in the middle. So this is defined as our median. You can see half are below and half are above. Up, what did I do? And that's it. That is the dividing line between the lowest and the highest. By the way, if you remember that when we calculated the mean for the sample, it was also 2. That is just a coincidence. In other words, it doesn't have to work that way. The mean and the median do not have to be equal. It worked out that way here, but it often does not. Now we're going to see later on how to interpret that relationship between the mean and the median. But for here, I just wanted to point out that the mean and the median turned out to be the same number, but it doesn't always work out that way. Now, what about an even number of elements? Like here, what do we do now? Well, we'll sort them. And then we'll have 0, 1, 2, 3, 4, and 6. So what do we do now? There's nothing in the middle. These 2 are in the middle. But there isn't a single element in the center of our data. What do we do now? Well, here's the approach taken by statisticians. Instead of picking one or the other, we average them out. So that 2.5 is now the median of this sample. And you can see it works because half the observations are below 2.5 and half are above. So those are the 2 cases. Okay, and here it is. So we'll just quickly summarize that. So if there were a data set with an odd number of values, median is the middle observation. And that's all there is to it. For a data set with an even number of values, the median is the average of the middle two observations. And that's it. That's all you have to remember. Huh, okay. By the way, unlike the last example with the means, here's one of the quirky things about the median. There is no formula for the median. There isn't one. How would you write a formula for something like that? Well, you can't. Furthermore, the procedure is the same whether the data set is a sample or a population. So they are the same thing. In other words, it makes no difference when you're doing medians. It makes no difference if it's a sample or a population. Okay. Now, that raises an interesting question. Why would you use the median instead of the mean? Why don't we just always use the mean? What's the point of even having a median in the first place? Well, we're going to see in a second that there are certain conditions under which the median is a better choice than the mean. Otherwise, we wouldn't use it. Okay, so it must be the case, because they both are used, that there are certain conditions under which one is a better choice than the other. So it turns out that the median is a better choice when our data contains something called an outlier. What exactly is an outlier? Well, you may already have a sense of what that means. But what this really refers to is this. An outlier is an element in a data set that is either substantially larger than the other elements or substantially smaller than the other elements. Okay. So let's say you have this scenario. Suppose that in a small neighborhood, the prices of the houses are, all right, we got one worth 500,000, 450, 550, and I don't know, 600,000. All right, fine. Now, for God only knows why, Bill Gates suddenly decides to build a house in this neighborhood. Okay. But he's not going to want a $500,000 house unless he uses it to store all of his golf clubs or something. So Bill Gates has a $20 million house built in this neighborhood. Well, that means that our sample now consists of these values and the 220 million. So you can see So I think it's pretty clear that that's an outlier, right? Okay, now it can go the other way around too. There can be a very small value as well that could be considered an outlier. Oh, let's say that oh, okay, how about this? A group of golfers, handicaps are 30, 20, 25, 40. And then there's somebody in that room who's really good and his handicap is 1. Oh my God, he's a pro. Okay, how did he get into that golf club? We don't know. Or how did the others get in? And I mean, I'm not a golfer or anything, but it means that when you're playing somebody else with a different skill level, this is something that's meant to equalize it. So you have a reasonable chance of winning. So the higher your handicap, the worse a player you are. So in this group, you wonder who is this, Tiger Woods or something? In this group, the handicap of 1 would be considered to be an outlier. And that's because it's so much smaller than the others. Now, you're probably wondering, well, how do we decide what does and does not constitute an outlier? Well, there are different ways of establishing a range of values that could be considered outliers. We're going to see one of them in this chapter, by the way. Okay, there's a certain amount of judgment involved, but there's going to be some points that we have to reach in order to be an outlier. Like, for example, let's go back to the houses. And you look at these prices, would you define 900,000 as an outlier? Well, it's hard to say because that's more than the others, but it's not that much more. It's not like $20 million. So we'll see fairly soon in chapter 3 how to formally define the ranges that define an outlier. In other words, how high does a value have to go to be an outlier, or how low does it have to go? So that way we're not guessing. Okay. I mean, these are extreme cases, the ones I'm showing you here. But it's not always that open and dry. Like here, what about a handicap of 10? Would that be considered an outlier? It's hard to say without those boundaries that we will define later on. Anyway, or here's a quickie example. We have somebody who's sailing along throughout the semester, and all of a sudden they get a 48 at the end in the final. Well, might want to think of that as an outlier. In others, maybe they're having a bad day, maybe they weren't feeling that well. It does not reflect how well they've done up to this point. So you can think of that as an outlier. It means that something's probably wrong. Or now here's an interesting example that I cooked up. Suppose that you're in your class and somebody in the neighborhood who's just retired, he's the vice president of some big corporation, he's got money like you wouldn't believe, but he never finished his college degree and he always regretted it. He comes back and signs up for Stats 1 at Fordham University. And so there's your class. These are all the ages of the students sitting around. And there's this 75-year-old who's in the class. Well, I would say that could be considered an outlier. Okay. And some people do that. When they retire, they go back to school and they take classes that they never had a chance to take. It does happen. Sounds like an interesting idea. I'm not sure if you would take stats if you were retired, but you might take something else. You might take like art history or something fun. But anyway, that could be defined as an outlier because that person is clearly much older than everyone else. Or now here's one using the data we've had up to this point, or something similar. This is our sample. Well, I think it's pretty obvious that this 100 is our outlier. Anyway, so we're going to pursue this example. Now, by the way, I don't think I mentioned this earlier. What I'm going to do with these recordings is, I think the optimal amount of time is to have them 1 hour in length each, roughly, because that's the perfect amount of time to be focusing on a topic. So I'm going to produce a series of these 1 hour videos throughout the semester. And I don't know exactly how many I'm going to need. It's hard to say compared to the classroom, but I will make sure that we have enough of these that we're covering all of the material, because we do only have, I think, 4 weeks. And so I'll be making a series of these, and you can look out for them on Blackboard. If I remember correctly, there's plenty of storage space in Blackboard for videos. If not, I can keep them on my YouTube page, but I'll make an announcement and let you know what's going on with that. But so we'll stop this right here. I think there's a perfect opportunity to stop, so we can look at this example from start to finish. And then the next recording will take this material and pick it up from there. So by the time we're done, you'll have the whole experience as if you'd been in the classroom all this time. It's just that you can sort of watch these when you get a chance, when you get home from work, or whatever the case may be. And that way, it doesn't matter what your schedule looks like, you can still get all the work done. Okay. All right. So I'll see you all next time.